Welcome everyone. My name is Michael Sitar, and today's webinar features RIEGL innovations, product introductions, and updates as announced at the Intergeo conference in Berlin this past month in the field of airborne laser scanning. Data sheets for some of the sensors introduced in the webinar are included in the handouts tab of the GoToWebinar browser, so please feel free to download these at your convenience. Alternatively, you can access all our product data sheets at our website at www.riegl.com. The webinar duration is about 30 minutes, and there will be an opportunity to ask questions at the end of the presentation. And for those questions not addressed during this webinar, they will be responded to individually in the following days, and a copy of the recording will also be made available to those that have registered. Now, many of you may already be familiar with this slide, but it's clear that it continues to grow. With the recent introduction of further new airborne laser scanning solutions this year, RIEGL's ALS product portfolio now offers a solution for virtually any survey application or payload requirement. These include hybrid large format laser scanners with internal high resolution metric cameras for wide area collection within an aircraft, multi-directional scanners for corridor applications when configured with a helipod, as well as standalone scanners for custom integration with third-party peripherals and enabling technologies. This extensive selection of sensor models means that payloads can be optimally configured to provide the highest quality and comprehensive data coverages from a large variety of aerial platforms. However, before we go into detail on these and other announcements, why is it that RIEGL is so prolific in terms of new product introductions and sensor releases? What exactly are our motivations for doing so? Well, let's consider the following contributing factors. The first is innovation. By developing new functionality, our consumers and customers can reduce their operational costs, minimize the opportunity for error, and simply make work and related processes easier and more cost-effective. Higher productivity translates to improvements in profit margins. New sensor configurations enable new applications and business models where competition may be limited. The second are customer demands to remain competitive as requirements for point density accuracy go up, but also the need to adhere to evolving standards of performance and safety compliance. The third is probably the most relevant to a sensor developer, and that has to do with component life cycles and their impact to continuing manufacturing. Parts obsolescence is a constant challenge in this age of rapid technology advancement, as well as supply chain availability. Improvements in core technologies that yield higher detector sensitivities, further laser range, and emission rate increases allow entry-level sensors to move up the value chain in terms of their price-performance ratio as their base technologies improve over time. Similarly, new advances in supporting or enabling technologies such as processor speeds and computing performance, data storage devices, and formats can have a significant impact to overall productivity. So with that being said, there are several sensors of similar capability and configuration within RIEGL's large format sensor series. Therefore, what models should one consider and for what applications or requirements? Well, that might be better understood if we first look at the key differences among them, in particular the VQ1260, 1460, and 1560 Mark IIs hybrid 3D imaging sensors. Firstly, it is important to recognize that there has been a tremendous increase in productivity over the last 10 years. In fact, this can be attributed in large part to the introduction of flash LiDAR technologies to the commercial survey market. Although primarily offered as a service, it did push traditional LiDAR manufacturers to explore the limits of performance with the introduction of dual laser systems, multi-pulse technologies, and further laser emission rate increases to close the gap in terms of both resolution and productivity. So much so that it is possible to collect almost 1,000 square kilometers an hour at 8 points per meter squared using the industry's most productive linear mode wide area mapping sensor, the VQ1460. So if mowing the lawn is your objective, then this really is the sensor for you. But what are the differences between these three sensors, and why might I choose one over the other? Well, to start, there are primarily two distinct scan geometry choices. The first is the traditional matrix pattern. The single matrix pattern is exemplified by the VQ1260 with its single laser configuration and is consistent with other RIEGL laser scanners that employ a unidirectional scanning mirror that creates a uniformly spaced parallel scan lines over ground. What is important about this is that as uniformly distributed point cloud means that AI algorithms can operate just as effectively and with similar search criteria and success at the FOV extremities or scan ends as at nadir. This is immensely valuable for automated classification routines such that the entire swath width is considered usable. There is no requirement for scanned endpoint decimation to normally distribute the points prior to the application of AI-based search criteria and feature extraction. The double matrix of the VQ1460 is simply the combination of two dependent lasers that are alternating their emissions such that they give the appearance of a single matrix on ground. The second is RIEGL's innovative and unique crossfire scan pattern that merges two independent matrix scan patterns to create a randomized but homogeneously distributed point cloud by leveraging two laser beam channels with counter-rotated and pitch scan geometries. This scan geometry has enabled the VQ1560 to be considered as the preferred sensor for low altitude corridor work, where high point densities can be realized at speed from an aircraft, but also that by flying offset to the asset, the fore-aft look angles of the opposing beam channels can provide increased vertical target coverage and density both ahead of and behind the flight direction. But why use a large format scanner such as the VQ1560 for low altitude corridor work? Well, firstly, the operational cost associated with an aircraft is typically much cheaper than that of a helicopter. Faster flight speeds also mean greater corridor lengths can be surveyed in a given mission. Furthermore, the higher flight altitudes provide an element of safety by providing a larger distance between the asset and the aircraft platform over a transmission right-of-way. This example shows LiDAR data collected from a VQ1560 at 50 points per meter squared and 120 knots over residential area, where the primary objective was to map all wire assets, including distribution, service, and pole guidelines. The raw data is first classified and then the assets vectorized, in this case using Pointera's automated AI algorithms for rapid data analysis. Productivity, higher flight altitudes, and the crossfire scan geometry associated with the VQ1560 make this sensor an ideal instrument for flying power line assets, whether it's transmission corridors or more traditional block surveys over urban and residential areas for distribution and service line mapping initiatives. The latest hybrid scanners from RIEGL are built on RIEGL's next generation architecture platform, enabling a direct upgrade path from single to dual channel capability and a doubling of the possible point density. This new architecture supports more returns per emission and ever higher pulse repetition rates. However, why should someone choose the VQ12 or 1460 over similar hybrid sensors in the wide area segment? Some unique benefits of the VQ12 and 1460 include a direct upgrade path from a single channel to dual channel system for scalable performance, the highest laser emission rates and productivity in the segment for maximum point density and overall collection productivity, a smaller installation footprint resulting from the inclusion of onboard data storage and the removal of external data recorders, a side-by-side dual camera arrangement for the inclusion of a dual cam high resolution RGB imaging system, such as the Phase 1 PAS280, a unique optical geometry that minimizes the atmospheric and noise points commonly found in similar long ranges, and numerous other innovative features and benefits. For those that are interested in what the data might look like from the VQ1460 wide area scanning system, there are some sample data sets available in the provided link. And also you will be able to access this through the recording at the end of the webinar. Now, unlike the newly released VQ1260 and 1460 sensors, which have integrated onboard removable data storage on the sensor itself, the current line of VQ series sensors utilize an external data recorder to capture LiDAR data in either online waveform or discrete data formats, full waveform capture, or both. And as a result of component obsolescence, such as the COM Express motherboard, but also due to evolving changes in electrical optic interfaces, an updated recorder is now available for the VQ series sensors. This recorder incorporates a new electronics platform, graphical user interface, and expanded data storage options. Similarly, a new VQ-IU or interface unit is being introduced that will allow the simultaneous storage of both LiDAR and camera data to removable SSD data cartridges. It will incorporate an internal PC with a Windows operating system. It is possible to install numerous applications, including the sensor acquisition software RIEGL, as well as third-party software such as IX Capture. The IU includes 4 high-speed 10G Ethernet connections, as well as up to 5 USB 3.1 ports for peripheral camera support. Now, the popular VUX 240 compact scanner was first introduced in 2018, and new for 2023 and 2024 is a redesign of the internal hardware and electronics platform, but with the same external dimensions. The pulse repetition rate has been improved from 2 to 2.4 megahertz over the previous model, but more importantly, the line speed has significantly increased by up to 50%, from 400 to now 600 lines per second. And this will enable the uniform point distribution across the entirety of the scan, high laser emission rates, and faster platform speeds. Increased output power supports higher point density at higher altitudes, but also superior detection of partial footprint returns on wires. And the camera control interfaces are now fully integrated, as well as an optionally embedded OEM INS GNSS board stack. So based on the successful introduction of the VUX 120 and VUX 160 multi-directional laser scanners and their innovative nadir forward, backward, oblique scanning capability, comes a brand new sensor that features not 3, but 5 scanning directions. This advanced instrument incorporates a 60-degree across track and 40-degree along track coverage capability with a pulse repetition rate of 2.4 megahertz and an exceptional line speed of 500 lines per second. Interfaces for up to 6 independent cameras are included and can be delivered as a standalone scanner only or as a turnkey solution with OEM INS GNSS systems and the supporting flight management solution, external data storage, such as the VQ-IU introduced earlier. The small laser aperture enables fitment into smaller diameter gyrostabilized mounts, such as the GSM 400 at under 27 centimeters or 11 inches in diameter. A closer look at the scanning geometry of the VQ680 is demonstrated here. Targets ahead of, behind, immediately below, and to either side of the sensor are rigorously covered for virtually occlusion-free data sets for superior coverage required for accurate urban modeling and the creation of complex digital twins. In terms of what is possible from a point density perspective, this chart demonstrates 8 points per meter squared collected from 1,500 meters AGL and 110 knots. And this provides an area coverage rate of approximately 280 square kilometers per hour. Of course, this is much easier to determine via RIEGL's RIE parameter software, as opposed to trying to analyze data sheets and point density charts. So simply plug in your point density requirements and your aircraft specifics, and the software will automatically determine the required sensor parameters, ensuring equidistant point spacing considering the full FOV. While many of RIEGL's airborne sensors are available as either turnkey solutions or standalone scanners, the VQ680 is also available as an OEM sensor module for direct integration into hybrid sensor configurations. The OEM version, or Systems Integration Edition, comes devoid of the active cooling mechanisms and extraneous housings for maximum size reduction. The vertical arrangement of the optical chassis and electronics platform seeks to minimize the aperture footprint to enable multi-sensor integration into a sensor aircraft portal. A first implementation is soon to be available from Vexcel in their recently announced UltraCam Dragon 4.1 for high-resolution 3D oblique mapping of urban centers and complex environments. The occlusion-free scanning geometry of the embedded VQ680 OEM module will provide best-in-class LiDAR scene coverage, enabling superior high-accuracy hybrid data sets and digital twins. Now, while RIEGL has sensors that are primarily designed for aircraft installations, we also have a broad portfolio of external pod solutions. The popularity of RIEGL's original VP1 helipod has meant an expansion of this series to accommodate more sensors and with configurable sensor orientations for varying application requirements, particularly as it relates to corridor and infrastructure mapping initiatives. The newer VPX1 pod enables hybrid sensor configurations with up to 3 supporting imaging sensors combined with a laser scanner and high accuracy GNSS-INSS system within the same enclosure. This line of portable pod solutions has been further expanded to now include the external aircraft installation via the VQX wing pod onto Cessna 172, 182, and 206 aircraft. And new for 2023 is the introduction of the VQX2 helipod that supports up to 5 cameras and the larger single-channel laser scanners for mid to high altitude collections. All the pods use the same dovetail quick connect system for rapid installation and removal of the pods from a large number of available helicopter and aircraft models. The VQX2 helipod includes an EASA STC and supports a wide variety of scanners, ranging from the small multi-directional VUX 120 all the way up to the single-channel VQ 780 Mark IIs. Seen here on a Eurocopter, the installation package includes not only the pod, but also the supporting mount for a complete turnkey solution. With the introduction of the VPX1 pod a couple years ago and now the new VQX helicopter and aircraft pods, virtually any RIEGL, VUX, and VQ single-channel laser scanner can now be combined with cameras of various image orientations and GNSS-INS systems, such that most all corridor and oblique mapping application requirements can be addressed directly by a RIEGL pod solution. Offered as a turnkey commercial off-the-shelf solution with all required system components and software, the RIEGL pod solutions are exemplified by the VPX1 with a VUX 160 multi-directional laser scanner in combination with 3 cameras, whereby simultaneous fore, aft, and nadir target coverages are possible from both the LiDAR and the imaging sensors. Similarly, the camera oblique angles can be further defined between ±30 and ±45 degrees, as well as an alternative configuration option featuring a 4-band nadir orientation with forward oblique. Such a scalable and flexible sensor platform has meant that the VPX and VQX pods can be configured to address a wide variety of applications. And these include, but are not limited to, power line mapping, high resolution forestry mapping, and even geological 3D exploration in combination with gravimetric towbirds. Finally, a quick update regarding the STC validation process associated with our new VQX wing pod for the Cessna 172, 182, 206 small aircraft. So the EASA, as we've mentioned before, that STC is now in hand, and FAA validation is currently in process. So USA users can opt to pursue a local approval with the supplied documentation ahead of the formal FAA validation if desired. Following this, RIEGL will be further submitting documentation to Transport Canada and the Australian Civil Aviation Authority. Now, first installations will require the expertise of a Part 66 licensed engineer or Part 145 maintenance organization. However, subsequent removal and reattachment of the pod by the pilot and or the survey staff will no longer require the service. But to be clear, this STC is a wholly complete effort. It covers every aspect of the installation, including all wire routing, the required power supplies, GNSS antenna mounting, and interior accessory installation. There is nothing left for the customer to pursue and is the only STC like it available anywhere in terms of the scope for the Cessna aircraft. And so in conclusion, RIEGL has developed a comprehensive portfolio of airborne laser scanners and solutions. The announcements today have largely filled any remaining portfolio gaps, enabling both service providers, integrators, and OEMs alike. And we look forward to evolving our product lines in line with industry trends and customer demands, as well as supporting all our clients with competitive and innovative solutions in the years to come. So thank you so much for your time and attention. And at this point, I'll open up the floor to questions. And I must have done a good job because right now I don't have any specific questions. So with that, thanks everybody for listening in. Like I said earlier at the beginning of the broadcast, we will have a recording that's available. And if you do have any questions or follow-up queries, you can address them to myself, MSITAR at RIEGLusa.com, or to sales@RIEGLusa.com, and we'll be sure to respond as quickly as possible. Have a great day, everyone, and thank you once again.